Hello, welcome to this new video from Guidance Education channel. We are continuing class 12 chemistry, chapter 9, coordination complexes. The subtopic is crystal field theory. Crystal field splitting energies. We have already discussed crystal field splitting energy for octahedral complexes. In this video, we will discuss crystal field splitting energy for tetrahedral and square planar coordination entities. Compare them with the crystal field splitting energy for octahedral complexes. Before we go into the details, please watch the video completely so that you get all points cleared. And if you think the video is useful, do like the video, share the video with your friends, leave your feedbacks as comments. If you have not yet subscribed my channel, do subscribe my channel. Also press the bell button near it so that you get intimated as soon as new videos are posted. Thank you very much. We will first recall the energy diagram for crystal field splitting energy in the case of octahedral complexes. In octahedral complexes, there are 6 ligands. This is the ground state of the 5d orbitals of the central metal atom. This is the excited state. When the ligands approach these d orbitals, then it gets split up into 2 sets. 3 orbitals at a lower energy level, which are called T2G orbitals, and 2 orbitals with higher energy level, which are called EG orbitals. The average energy of the excited 5 orbitals is called the barycenter, and it is taken as 0. The difference in the energy of these 2 sets of orbitals is a crystal field splitting energy represented as delta O, O for octahedral. The crystal field splitting energy for octahedral complexes is much greater than pairing energy. Therefore, pairing of electrons take place. I have already discussed these topics in detail in previous videos. Please watch them so that you understand this concept well. The 3 T2G orbitals are dxy, dyz and dxz. These lower energy level orbitals are degenerate. The 2 high energy level Eg orbitals are dx square minus y square and dz square. These 2 are also degenerate but at a higher energy level. I will complete this energy diagram for octahedral entities. Now we will take up tetrahedral coordination entities and compare its crystal field splitting energy with that of octahedral. The energy diagram is given there. In the case of tetrahedral coordination entities, the T2G orbitals which are at a lower energy level in the case of octahedral complexes gets reversed in the case of tetrahedral coordination entities and becomes higher energy levels, and the Eg orbitals which are at higher energy level in octahedral complexes becomes lower energy level orbitals in the case of tetrahedral complexes. In tetrahedral coordination entities, there are 4 ligands. The pattern of splitting is reversed in this case. dxy, dyz and dxz are at higher energy level, and dx square minus y square and dz square are at lower energy level. There are 2 lines here. These are the 2 orbitals. There are 3 lines here. These are the 3 orbitals. That is why we say that the pattern of splitting of crystal field in tetrahedral complexes is just the reverse of what you find in the case of octahedral complex. Crystal field splitting energy for tetrahedral coordination entities can be represented as delta T. From the diagram you can understand the delta T is much less than delta O. You already know that pairing of electrons in the d orbitals depends upon the relative magnitudes of pairing energy and crystal field splitting energy. If crystal field energy is greater than pairing energy, the electron will enter the higher energy level only after pairing the electrons in the lower energy levels. In the case of tetrahedral coordination entities, since the crystal field splitting energy is very low, pairing does not take place. So after the lower energy levels are filled up by one electron each, the next electron passes directly into the higher energy level. In the case of tetrahedral coordination entities, the four ligands approach the central metal atom in between the direction of the lobes of the orbitals. Therefore, the repulsion will be very low. That is why the crystal field splitting energy is low. It has been estimated that delta T is equal to 4 by 9th of the crystal field splitting energy for octahedral complexes. That is delta O. So, the tetrahedral coordination entities give rise to high spin configuration. I have already explained high spin and low spin complexes in previous videos. Please watch them. So, I have explained why tetrahedral coordination entities have low crystal field splitting energy, why they give rise to high spin complexes. Always remember that delta T is much less than delta O. Now the crystal field splitting energy for square planar coordination entities and its energy diagram. This is more complex than the other two types. This is more complex than crystal field splitting energy for tetrahedral or octahedral, but it can be easily understood when we compare this with the crystal field splitting energy for octahedral complexes. The two EG orbitals dx square minus y square and dz square, which are degenerate in the case of octahedral complexes, is no longer degenerate in the case of square planar complexes. Dx square minus y square has the greatest energy in this case. Dz square orbital has less energy than the average energy. It has a minus value. Among the three degenerate orbitals of the T2G in octahedral, dxz and dyz remain degenerate in square planar coordination entities. They have the least energy. What remains is the dxy orbital, and it is at a higher level than dz square orbital, and it has energy almost same as the average energy of the octahedral complexes. I think you can remember this easily now. So dx square minus y square has the greatest energy, then comes dxy, then dz square, then the remaining two dxz and dyz has the least energy. These two are degenerate. Now we have to explain why the energy splitting pattern is like this. Dx square minus y square orbital has the greatest energy because it is directed directly, or it is pointing directly towards the approaching ligand. So there is lot of repulsion. Because of this repulsion, its energy gets boosted up tremendously. The dxy orbital lies in between the ligands in a plane with the ligand. So that orbital also experiences repulsion, but less than the repulsion experienced by dx square minus y square. So its energy is a little less than the energy of the dx square minus y square. When we consider dz square, which is at an energy level less than that of dxy, the lobes of the dz square orbital points outside the plane of the complex. The compound is square planar. So these lobes are pointing outside this plane. Hope you remember the shape of the dz square orbital. It is donut shaped. There is a central belt-like portion and two lobes pointing outwards, one upward and one downward if we show it in the vertical plane. These are the two lobes. This is the central belt region. Though the two lobes are directed outside the plane of the complex, the central belt region is in the plane of the compound. So it also experiences some repulsion and it has some energy, though at a lower level. And when we come to dxz and dyz orbitals, they lie totally outside the plane of the compound. Therefore, they experience least repulsion. So, they possess the least energy. Since the repulsion is less, electrons will first enter these two orbitals. The energy difference between the least energy and the highest energy level in the crystal field splitting is called crystal field splitting energy. And in this case, you can notice that the crystal field splitting energy for square planar compounds represented as delta S is much greater than the crystal field splitting for octahedral complexes, that is delta O. I will mark delta S here. You may complete the energy diagram for square planar. So you have the energy diagram for tetrahedral, square planar and octahedral complexes. Hope you are benefited by this video. Do not forget to subscribe, like, share and also leave your feedbacks as comments in the comment box below. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.